Okay, today we are finding solutions of polynomial equations, or roots. The directions say here, find all roots for each of the following equations. If a root has a multiplicity greater than 1, state its multiplicity. We'll talk about what multiplicity is in just a little bit. But basically what we're going to be doing is factoring these and then using the zero product rule to find the solutions or roots. So number one, and with any kind of factoring situation, you want to ask yourself, is there a common term I can take out? Yes, I can take out an x here. So x times x squared is x to the third. X times 7 is 7x. Then this is as factored as we can get it. We can't break down this any further. So we think about what would make each piece equal to 0. So in other words, we go, okay, how could x be 0? Well, that's it. X is 0. That's one of the solutions. And then we think about how could x squared plus 7 equals 0? Well, we just solved this little mini equation here. We take away 7 on both sides. We get x squared equals negative 7. Take the square root of both sides. We get x equals positive or negative square root of negative 7. Now remember, since we have a square root of a negative number, we can take out I. That represents square root of negative 1. So that's as far as we can simplify this one. So we have 3 roots or solutions: 0, and then negative I root 7 and positive I root 7. You could go ahead and keep them as positive or negative. That's fine. There's just one way to write it. Okay, you guys go ahead and do number 2. Okay, here's what I got for number 2. I got 3 real answers this time. Over here we did have 1 real answer and 2 imaginary answers. Yeah, because when we added the 5 here, we got a positive, right? So anyways, we got 3 real solutions. You can list it out like this, or if you did 0 and then positive or negative square root of 5, that's fine. Okay, let's take a look at number 3. We can't take anything out of all 3 terms. It's a trinomial, so let me see if I can use this method to find 2 numbers that multiply to 1 and add up to negative 2. So something times something equals 1, and those same 2 things have to equal negative 2. Yep, that'll work. Negative 1 and negative 1. So that means I can break this down into x to the third minus 1 times x to the third minus 1 equals 0. Okay? And different ways we could handle this. You might be tempted at this point to just call this x to the third minus 1 squared. What I'm going to do, though, before I do something like that, is take this, and I'm actually going to break it down further, because I noticed that it's a difference of cubes. So if you have a difference of cubes, that can be rewritten as a minus b times a squared plus ab plus b squared. Okay, and so in our case here, a is just going to be the cube root of x cubed, which is x, and the cube root of 1 is what b is going to be, and that's just 1. Okay, so in other words, a is x, b is 1. All right, so now we're going to end up with a minus b, so x minus 1. And then we're also going to have x squared, because we have a squared, x squared, plus ab, so x times 1 is just x. And then plus b squared would just be 1. Okay, now we have this twice. So we have it here also. So in other words, we could think of it like this whole thing is squared. Okay, like this. I'm going to use kind of brackets to show that. But probably a less confusing way to write this would be like this. Okay, so yeah, again, the squareds here come from the fact we have two of these. All right. So now these are broken down as much as we can break them down. Let's think about what our answers would be. Let me take that first piece. X minus 1 could equal 0, right? I'm using the zero product property. Add 1 to both sides. We get x equals 1. So that's one of the solutions. The other solution, unfortunately, we're going to have to use the quadratic formula for because we have a quadratic to solve here. So a, b, and c are all just 1. So I'm not going to write that out, but we're going to have negative 1, negative b, plus or minus b squared, which 1 squared is just 1, minus 4 times a times c. It's already squared that. That's why I didn't show the squared there. And then all over 2 times a. A is 1, times 2 would be 2. Okay, simplifying this a little bit, this is going to come out to 1 minus 4, which is negative 3. So I'm going to have the square root of negative 3, but then taking out the negative, I end up with that. I'm trying to save a little room here. So I have negative 1 plus or minus I root 3 over 2. Now, okay, so my solutions here, before we write them down, we actually have each of these solutions twice. Why do we have them twice? Well, it's because this squared here. Now, we don't say we have the solution twice. That was just my informal way of saying it. We say that we have this solution here, this root, has multiplicity 2. Has multiplicity 2 because, in a way, we have this solution twice. So we would say 1 is one of our answers, and then we can just abbreviate mult 2 like that. So 1 multiplicity 2. And then we also have, I'm going to go ahead and separate these out just to be clear. I have negative 1 plus I root 3 over 2, and I have 2 of those, again, because this part of it was squared. So that has multiplicity 2. And then I also have, you know, the minus version here. That also has multiplicity 2. Okay, so yeah, you're going to have multiplicities mentioned if in your factored form you have exponents greater than 1 on your individual factors. And it's just going to be whatever that number is. Okay, so, all right. You guys go ahead and do number 4. Okay, so here are my answers. I have I times the square root of 7, multiplicity 2, again because of the 2 here. I just, when I use the zero product property, I just kind of took this off to the side, but I'm going to have these are 2 answers here, but I'm going to have each of those twice because this factor is repeated twice. So I just separated it out. I did the positive I root 7, that has a multiplicity of 2, and then the negative I root 7, multiplicity 2. If you kept it as positive or negative I root 7, multiplicity 2, it'd be okay. To me, that's a little confusing writing it down that way. It makes a little bit more sense to separate it out. All right, so let's take a look at number 5. Again, you always want to check to see if you can take something out. I didn't mention that in number 3, but you couldn't have in number 3. But in number 5, you can take out an x. So I'm going to do that. X times x to the third is x to the fourth. X times negative 64 is negative 64x. Okay, so we have, now we also have a difference of cubes here, which I talked about before. This time, my a is the cube root of x cubed, which is x. B is the cube root of 64, which is 4. Again, to do that in your calculator, you could go 64 to the 1/3 power, and you get 4. So we're going to end up with that x just comes down there, and then we're going to have x minus 4 using the same formula from up here, okay? And then we're going to have x squared plus ab, so meaning a times b, so x times 4 is 4x. And then b squared, 4 squared would be 16. Okay, so one of our solutions is going to be 0, right? Because we have that x out front. The other solution, x minus 4 equals 0. You could solve it or just think, well, 4 minus 4 is 0, right? So x equals 4 is another solution. The other one, we have a quadratic factor. We have to use the quadratic formula. A equals 1, B equals 4, C equals 16. So we're going to go negative b plus or minus square root b squared minus 4 times a times c all over 2 times a, which that would just be 2, right? 2 times 1. Okay, let me simplify this a little bit here. I'm going to go ahead and grab a calculator and put the discriminant in. That's the inside of the square root. So 4 squared minus 4 times 1 times 16 gives me negative 48. So square root negative 48 over 2. This is going to reduce to, we're going to have an I, and then, well, let me just think of that off to the side here, if I can squeeze it in. So I'll have I root 48, and then 16 is the biggest perfect square that goes into that. Goes in 3 times, so you get 4I root 3. So negative 4 plus or minus 4I times the square root of 3 all over 2, and then 2 divides into both of those. You get negative 2 plus or minus 2I times the square root of 3. So our final answer then is x equals 0, 4, when we have negative 2 plus 2I root 3, and negative 2 minus 2I root 3. All right, go ahead and do number 6. Okay, here's my answer for this one. I got 2, and then I got negative 1 plus or minus I times the square root of 3, which I separated out here. Okay, now what we're going to do is see, is there a relationship between the degree of a polynomial and the number of roots it has? Let's go ahead and fill out this table down here below. So number 1, let's fill out the degrees first. We had a degree of 3 in number 1, a degree of 3 in number 2. Let's write that down. In number 3, we had a degree of 6. In number 4, we had a degree of 4. And then in number 5, degree of 4. Number 6, degree of 3. Okay, let's see how many solutions or roots we had in each problem. Well, in the first one, we had 1, 2, 3. In the number 2, we had 1, 2, 3. You might see a pattern forming here. In number 3, we had, now with the ones with multiplicity 2, we count those twice. So 2, 4, 6, right? And once again, we count the ones with multiplicity 2 twice. So 2, 4. And then in number 5, we have 1, 2, 3, 4. And then number 6, 1, 2, 3. So, conclusion, the degree of the polynomial is the same as or equal to the number of roots that it has. So that leads us to the fundamental theorem of algebra. A polynomial of degree n has n complex roots, counted with multiplicity. All right, so you got to count the multiplicity in order to get to that same amount.